Hi all, today we'll look at digital electronic circuit design. In that, first of all, let's see what is a digital signal. It's an electrical signal that has two discrete values or levels. So these two levels can be called as the low level and the high level. At any given time, the digital signal will always be one of these two levels. Usually we refer to the high level as logic 1 and the low level as logic 0. We can illustrate this concept by using these diagrams. If you look at the first diagram, it's referring to the positive logic. In that, the low voltage will be taken as 0 and the high voltage will be taken as 5. But we will not get exactly 0 volt or exactly 5 volt all the time. Therefore, any value between 0 to 1.5 volt is taken as low voltage and any value between 3.5 volt to 5 volt will be taken as a high voltage. And we can have the opposite of that as well. That's called the negative logic. In that 0 to 1.5 volt will be taken as the high voltage and 3.5 to 5 volt will be taken as the low voltage. As we have an idea about a digital signal now, let's see what is a digital circuit. It's a circuit that processes digital signals. The important thing about a digital circuit is it operates in the binary mode. In that, each input and output voltage represents either 0 or 1. This characteristic of using either 0 or 1 in a digital circuit will enable us to use Boolean algebra in analyzing and designing digital circuits. The reason being that Boolean algebra is also having two inputs similar to a digital circuit. As we are going to use Boolean algebra in digital circuit design, let's look at the concepts of the Boolean algebra now. In normal algebra, we are using the decimal number system, which contains 10 variables. But in Boolean algebra, we are using the binary number system, which contains only 2 variables. And these variables are called Boolean variables. In decimal number system, the variables can take values from 0 to 9. But in Boolean algebra, we have only 2 states, that is either 0 or 1. Therefore, as an example, if x is a Boolean variable, then x is equal to 0 or x is equal to 1. Now that we have talked about the Boolean variables, let's look at the Boolean operations. Similar to the normal algebra, Boolean algebra is also having 3 basic operations. These are called AND operation, OR operation and NOT operation. Of that, the simplest operation is the NOT operation. Let's look at that now. This is also called the complementation. In this operation, whatever variable we use as the input will be complemented. That is, it will be changing the state. For an example, if you send the input as 0, then the output will be 1. On the other hand, if the input is 1, then the output will be 0. The next Boolean operation is the AND operation. We call it the logical multiplication. In that, we look at the logical multiplication of 2 Boolean variables. In this operation, if both variables are equal to 1, then only the output will be equal to 1. Otherwise, if at least one variable is equal to 0, then the output is going to be 0. The third Boolean operation is the OR operation, or we call it the logical addition. In that, if at least one variable is equal to 1, then the output is equal to 1. Now these are the 3 basic operations Boolean algebra is having. Now we will look at the Boolean algebra rules. First of all, there are 6 simple rules which are given here. Here x represents a Boolean variable. If you look at the first rule, it says x OR operated with 0 is equal to x again. Now, as I said earlier, this x can take only 2 values, that is either 0 or 1. Therefore, if x is going to be 0, in that case 0 or 0 is equal to 0. On the other hand, if x is equal to 1, then 1 or 0 is equal to 1. Similarly, if you look at the second rule, in that x or 1 is equal to 1. Here also we can input values to x and see what happens. If x is equal to 0, then 0 or 1 is equal to 1. Also, if x is equal to 1, then 1 over 1 is equal to 1. You can easily get these results by referring to the truth table of the OR operation, which I have given earlier. The next two rules, that is the rule number 3 and the rule number 4, are related to the AND operation. By referring to the truth table of an AND operation, we can verify these rules. Now, if you look at the third one, it says x AND operated with 0 is equal to 0. If you input the values to x, if x is equal to 0, 0 and 0 is equal to 0. Also, if x is equal to 1, 1 and 0 is also equal to 0. For the other three rules which are given here, that is x and 1 equal to x, x or x equal to x, and finally x and x equal to x, can be verified by referring to the truth table of OR and the AND operation. Next up, we'll look at some more Boolean algebra rules. In that, the number 7 is x OR operated with the complement of x is equal to 1. If you substitute the values to x and check, if x is equal to 0, then x complement will be equal to 1. Then the OR operation of 0 and 1 is equal to 1. Similarly, if you input the initial x value to be 1, then x complement will be 0. Therefore, again, the OR operation of 1 and 0 is equal to 1. If you look at the rule number 8, it says x AND operated with x complement is equal to 0. You can also verify this by inputting values to x. If x is equal to 0, x complemented is going to be 1 and the logical multiplication of 0 and 1 is equal to 0. Similarly, if the x value is 1, then the complement of x will be 0. Then the logical multiplication of 1 and 0 is also 0. The ninth rule is important. That's called the double complementation. That is, if you take a variable and if you complement it twice, then you will get the original variable back again. Therefore, x double complemented will be equal to x itself. Rule number 10 is the commutative law. That is, we can change the position of the variables over an operation. As an example, A OR operated with B is same as B OR operated with A. Similarly, AND operation of AB is same as the AND operation of BA. The next rule is the associative law. It says the order of the operation can be changed. If you look at the part A, that is the associative law for the OR operation. In that, we have A or B within brackets OR operated with C equal to A or B or C within brackets. As you know, whatever operation we have within brackets, we have to do first. Therefore, according to the associative law, if we do the A or B operation first, or if we do the B or C operation first, it doesn't matter. They are all equal to each other. In part B, we have the associative law for the AND operation. In that, A and B within brackets AND operated with C is equal to A and B and C within brackets. Here also the order can be changed. The 12th law is the distributive law. In this law we use both and OR operations. In the part A and B or C within bracket is equal to A and B or A and C. In this we have expanded the left hand side of the operation. Similarly, in part B, we have A OR operated with B and C brackets. When you expand it according to the distributive law, it will become A or B and A or C. Finally, we have two redundant laws. Part A of the first one is A or A and B is equal to A. Part B is A and A or B is also equal to A. Rule number 14 is also an important one. In that, we have a variable x OR operated with the complement of this x, that is x bar, and operated with a second variable y. this whole operation is equal to x or y. These redundant laws are extremely important to reduce Boolean expressions, which we'll be doing later. Now that we know the Boolean rules, let's try to prove some Boolean expressions. There are two ways of proving a Boolean expression. First one is using the perfect induction and the second one is using the Boolean algebra rules. First of all, we'll look at the perfect induction. In perfect induction, we use a truth table to verify the validity of all the possible combinations that a Boolean variable can take. I'll illustrate this using an example. There are three examples here. We'll do the first one using the perfect induction. It's one of the redundant laws we have looked at earlier. That is, x or x and y is equal to x. Here we are verifying the validity of all the input combinations with the output values. There are two variables in the input side, that is x and y. Therefore, we have two columns in perfect induction for the input combinations of x and y. Those combinations are 0, 0, 0, 1, 1, 0 and 1, 1. In the left hand side of this example, we have x and operated with y. Therefore, we have a xy column which states the AND operation of x with y. Then we have to operate this xy result with x variable again. Once you do that, you will get the fourth column as x or x and y. That is the left hand side of the expression, and the four values are 0, 0, 1, 1. Which in turn is equal to the input combinations of x variable, that is 0, 0, 1, 1. Therefore, you can see that all the values which we will get as the left hand side of the expression is equal to all the combinations we will get in the right hand side. As you know the perfect induction now, you can try out the other two examples using this method. Next, we will see how to prove a Boolean expression using Boolean rules. We will use the same example for this, that is x or x and y is equal to x. We'll start with the left hand side, that is x or x and y. You can see that x is common to both terms here. Therefore, we can take x out as a common factor. When we do that, we are left with x and 1 or y. But from the Boolean rules, you know that 1 or y is equal to 1. Therefore, we have x and 1, which is equal to x again from the Boolean algebra rules. That's equal to the right hand side. In this way, you can solve a Boolean expression by making use of the Boolean rules. You can try out the other two examples and solve them using Boolean rules. Once you finish those, you can try these examples. In this, if you look at the first example, from the first two terms, x bar y is common. Therefore, we can take them out. Once we take them out, z bar or z will be left, which is of course equal to 1. Similarly, from the last two terms, you can see that xz is common. Once we took it out, y bar or y is left, which is again equal to 1. Then the final answer is x bar y or xz. In the second example, we can expand all the values. And then you will have AB, O, AB, O, AC, O, BB, O, BC. From the Boolean rules, B and B is equal to just B. Therefore, we can write it out. And then you can see that for several terms, B is common. Thus, we take out B. Then you are left with within brackets A or 1 or C. As there is a 1, this entire expression will become 1. Then the final answer is B or AC. If you look at the third example, once you expand the last term, you will get x and x bar y or y bar and x bar y. From the Boolean rules, you know that x and x bar is equal to 0 as well as y bar and y is equal to 0. Thus, the last two terms of this expression will become 0. Then you are left with x or y bar or x bar y. From the redundance laws, you can see that x or x bar y is equal to x or y. Therefore, once we do that simplification, the Boolean expression will become x or y bar. Again you know y or y bar is equal to 1. Then you are left with x or 1 that is equal to 1. Thus, the final answer for this expression is 1. Once you finish this, you can try out these 4 examples. Use the Boolean algebra rules to simplify them. In the next video, we'll look at the De Morgan theorem, which can be used to simplify Boolean expressions even further.